Hi, everyone. Thanks very much for coming, especially since Roland is giving an Akka talk right now over there, so I'm really happy that anyone showed up at all. This is a new experience for me in that Darach is a Pony user, and he's giving the talk, and this is the first time someone who isn't part of the Pony development team that I know of is giving a talk on Pony, which is pretty exciting. On the other hand, he made the slides and showed them to me, and then I was like, great, these are wonderful. And now he's changed them all and refuses to show them to me. So what's going to happen next, I have absolutely no idea. Basically, Darach's going to run the show, and if you have questions, I'm happy to answer them, or if Darach wants to answer them, that's great too. I don't know if he's going to make me talk about specific stuff, and we'll find out. So let's go.
Have we got tone? Okay. Hello and welcome to his show that I'm giving. So apart from Pony being an actor language, I'll skip that. Pony's all about wombats. So as you're going to get to know in this talk, before this becomes natural to you, Pony's all about denial as a capability. So we need to get used to contrarian logic, which becomes normal after a couple of months of using Pony and 3 one-hour sessions with Sylvan that lasted about 8 hours, and we both got in trouble for getting home late, which is how this talk basically got constructed. So I'm the Padawan Pony, so I'm the learner. I'm just a geek who loves Pony. And this is Sylvan. He is the Pony master, the Uber Wombat, the brains behind this wonderful language. And for those of you that don't know, this is research out of Imperial College in London. So this is a London or West London-based technology. So that's pretty awesome to have at a London conference. So let's have a look. There'll be a fairly interesting agenda for this because Pony is such an interesting collection of things that there's like 10 different talks we can have about the language, but we only have time for one talk. So we're going to fit in 3. So we're going through the basics of the language so you get comfortable with the syntax. It's exactly like Erlang. It's a really nice syntax based on Fortran. Then we're going to do some benchmarking. Because everyone loves benchmarking, right? Especially micro benchmarking. We've got many experts in the audience. Some people say do, some people say don't. Then we're going to go through the actor model, which is why we're here. So this is the newest actor model in the pantheon of actor models that have been done. We've got the most successful actor model. We've got Joe here. And we've got the newest actor model from Sylvan here. So that's rather prescient. Pony's a bit weird in that it's a compiler-oriented let-it crash technology, only it lets it crash at compile time, thereby proving it can't crash at runtime. This had the strange effect that at runtime we do actually have errors, but it's okay, they're not like errors in Java, they're cheap. Because cheap is good and cheap runs fast. So there are no runtime exceptions in Pony, but I'm jumping ahead of the slides now to confuse him because it makes me happy. But Pony's still just a language. Erlang's actually a system. It's not just a language. So Pony OTP is like the kind of Pony that Joe might want to use. Because we know he's already fiddling. He's like user number 0.8. And then we go through Pony promises, because you all know futures are bad. So we're going to tell you what's around the corner in Pony based on some of the activity that's passed or happened over the past couple of weeks. Some of which may be our fault, your fault, or we don't know. It kind of happened together. And then we'll have a Q&A. Okay. So let's get through the basics. How many folk here are Erlang programmers or reasonably familiar with Erlang?
Awesome.
Or other languages like the imperative ones? We have 3 honest people in the audience. This is great. So Pony has variables. It has 2 types of variables. Variables that Joe's like to have single assignment. And so they're very easy to manage and think about. And we have kind of variables that are like the imperative variables that you can mutate and don't understand. Pony likes you to have a choice, so it gives you both. And we use the same syntax and fields that we use in classes. I just got that wrong. So if you want to make a variable private, you add an underscore. That's very, very nice, reasonable syntax. They're typed, so you can define a type against your variable. So this is a Boolean. This is a 64-bit signed integer. Very simple. Let's move on. We have expressions. So say given three variables, A, B, and C, values 1, 2, and 3. So if we have A plus B times C, can anyone tell me what we can't actually see the hints in here, which is terrible, but I'll remember. Is this going to give me 7 or 9? A plus B times C, come on, it's so simple. Who are the mathematicians in the audience? Hands up. Okay, we have 4 fearless mathematicians. What's the answer to this question? Don't tell them, computer scientists. Who thinks it's 7? Who thinks it's 9? Who isn't sure? At least 2 people are correct. So it can be 7 and it can be 9 depending. What's the problem here? What can't we see in this code? What is the syntax missing? Precedence. In most languages, precedence is done for you. In other words, you don't know which one they picked. In Pony, you have to provide the precedence. It's always correct.
By the way, in small talk, that's 9.
Because reasons. So we barely glanced at the surface of Pony and already realized this is something just a little bit different. So what about widening conversions? Who loves them? Hard to fool audience. Yes, there's none of that in Pony either. You have to explicitly cast. None of this we'll guess for you, because we'll guess wrong. So Pony is safe, you have to make a choice. It's really very simple. And we don't like statements. Statements are evil. In Pony, statements are expressions, so all statements return a value. It's very simple. Are there statements? No, they're expressions. The statements return a value. It's very simple. So for example, if we wanted to assign a value to x here, which is a single assignment, then we can totally do that conditionally if that was something we needed to do, which is very handy. So we could have a for loop. Yes, it also returns an answer. What answer does this one return? Can anyone tell me? It's going through a range of numbers between 1 and 10. It's kind of max exclusive. So what is the value returned by this for loop? Anyone want to stab a guess? Is it 7 or 9?
That's hard to read. Sorry about that.
Well, it's going from 1 to 10, max exclusive. 7 is irrelevant, right? It returns 9. Okay, very simple, very consistent. Okay, errors must be handled. Okay, it's let it crash, but the compiler does that, which means if it does crash, we have knowledge of where it will crash, so you can actually handle it safely. That's kind of a bit weird if you're used to writing Erlang, where anything can happen. We just ignore it because we let it crash, right? You can actually handle it reasonably in Pony. And because there's no runtime exceptions, anything that did crash you don't have access to, so you can only act on an error based on what happened before that didn't crash, so even your exceptions are safe and fast. That's kind of awesome. A number of ways you can handle exceptions. So anything in Pony where you can trap an error is kind of an else loop, so we can compensate by printing some statement or sending a message somewhere. We can actually propagate the error. If you propagate the error, the function syntax or an actor behavior, you have to say, I actually return an error. I may not complete. I'm partial. So we use a question mark to signify that. It's not here, so this actually won't compile. Remember, the compiler says no, so even if you think the code is reasonable, it knows you're unreasonable. It won't compile for you. It'll force you to go through again. Okay, or we can swallow the exception. I don't care. So in that case, it's handled because we didn't care. It's gone.
You can't change the background of all the images devices. I just can't read the code.
Yeah, this is tough.
I'm sorry about this. The screen doesn't agree with the.
You know what? I'm going to try
Try it.
quick hackery. Where's your editor?
There's no editor.
I'm not going to try quick hackery because there's no editor.
Okay.
The Mac has a reverse.
Oh, yeah. Just reverse the whole thing.
Hey, that'll work. How do I do that?
In accessibilities under settings.
System preferences.
Thank you, Rob.
I apologize for that, but it won't be readable.
Ugly is better than non-readable, so.
Oh, the man. Invert colors. Sweet.
Try it. Way, readable.
And the first talk. And the first post-talk point goes to Rob. Thank you very much. I'm glad I met you the other night, so I know your name. So we can just swallow the exception.
Yeah, let's back up.
Back to here. So here you can see.
All right, that's too.
Hey, but you know the answers now. It's not as funny. Okay, so we got variables. You have let, which are single assignment, just like her. Okay, skip. Okay, Joe gets annoyed. Skip. Yeah. Okay, widening. Awesome. Statements or expressions. We're all good. Okay, errors must be handled. Okay, there's 4 different types of this. We can handle it, consume it, not propagate the error because we're happy. We can handle it and propagate the error because we're definitely not happy. We don't know why we're not happy because when the error occurred, whatever caused the error means it's unsafe. So why would you want to propagate that? It's based on something that we don't know what we don't know about. We know it was erroneous, we don't know why. So we just say, yeah, there was an error. Deal with it. We don't have to deal with it, we're sort of passing it on. It's very simple. That's the complexity of error handling in Pony. It's pretty simple. And then we have the third case, is if something does happen, I still don't care. So if something going on happens, we know that we don't care, so just ignore it. It's very simple. Now, when we propagate, you can see we've added a question mark, so this means I'm partial. I may or may not fail. You deal with it. I don't care. You may care, but I certainly don't. So it's very, very simple. And we have Erlang style pattern matching. Does anyone know what this is who's not a functional programmer? Now, there were 3 admitted imperative programmers here. Can you help us out here? This is imperative syntax. Like if, then, else, if, then, else. It's horrible. It's illegible. I can't possibly understand what this stuff does. It's also extremely verbose. I mean, I don't know what this does. Anyone understand this? Yeah, the 3 imperative programmers, not everyone else. They've already figured it out. This is pretty obvious. This is pretty cool. So we have pattern matching syntax. So you can see we're doing a match. We're creating a tuple of A and B. Yes, we have tuples. Where A is greater than B, so we have guard expressions, and then we can return a value because it's a statement. Oh, which is an expression. Did I say statement? I meant expression. If something else happens that we didn't cover in our clauses, we have a default get out of jail free card, and we can do something else. So pattern matching is extremely simple. We also have wildcards. So if you don't care what this value happens to be, we can also handle that case. It's exactly the same as in the Erlang case. Underscore means I don't care. Where it gets interesting is we also have atoms, but atoms in Pony are a little bit different. So we call them primitives. So we have primitive red, green, and blue. If you're an Erlang programmer, you can think of this as an atom. The difference really is the algebraic type system that allows us to get a little bit more structured. So we can say red, green, and blue are atoms, but color is the set of red, green, and blue atoms. You can pick one, which is pretty nice. So we can create tuples of these, or we can union them, and we can have an optional use as well, where we can go, it may be a string, or it might be not a string. So pick either. This is pretty cool. So for example, in this case, we have the map from the standard library, and the key, for example, is hashable, or it's comparable. Okay, so that should be fairly obvious. So that's a key, and then this map is a hash map, so it's hashing on equality based on the key. Fairly simple, right? So we can destructure a tuple just like in Erlang. So in this case, we've got a tuple which is of type string color, and we can construct it in the usual way using parentheses. We can have member access, and we can, of course, destructure and pull out the individual values. Make sense? That's pretty simple. It's like totally Erlang, with the same funky syntax. It's awesome. But primitives are a little bit different. We can also, for example, package functions inside of primitives. So if you don't have anywhere good for a utility function to go, we can actually stick inside a primitive. So For the three imperative programmers, that means you can have things like monostates or utility or helper classes. It doesn't actually create anything, or it doesn't require any state in and of itself. It's just a useful place to stick a lonely function. So it can stay with its lonely functions that are related to the same kind of thing you want to do, IO utilities and stuff like that. They're also used to represent the built-in types. Okay? We have traits. So this is nominal typing. So if you want to describe things in the usual way, and again, this imperative language people, this is for you. So you can do all of that good stuff. So this is traits in mixed sense, as in the Scala sense. And we have interfaces. And unlike interfaces for the imperative folk, these are structural subtypes. So for example, in the standard library, we have a definition of a real number. And we have this function add. So if we have an add function that conforms to the same basic structure, then we can use this to, for example, in a pair, we overload add, and we can use plus to add pairs. So that's all built in. So we've got operator overloading, and we've got structural subtyping, which is using operator overloading. So if it conforms to the shape, you're good to go. And this is fairly useful if you want to be flexible. If you want to be inflexible, you can use traits if you want to enforce some discipline over how the categories are composed in your system, which is very, very flexible and powerful to have both and use which one as you need it. We have classes too. Slight difference here. There is no multiple inheritance from the extension perspective, so there's only one line of inheritance, which is from something that's either an interface or a trait or some algebraic type composition of those things, which again leads to a very fine grain of control. Very simple, so nothing you haven't seen before. Okay, so here we have a class Wombat, and Wombat has a name. The name can be initialized once and only once in the constructor, or by default. For example, in hunger level, we're defaulting hunger level to 0. Okay, so we have constructors. So you can have as many constructors as you want. You use the new keyword to create a new constructor. That's basically it. They don't have to have any specific name. If you call it create, you don't actually have to use the .create syntax to call it a constructor. You just invoke a new type by using the type name. So we'll have an example of that in a second. Okay, so for example, we have a Wombat, which is a class that's using a nominal type called named, and its name is Sylvan by default. Does that make sense? Or no, its name is Sylvan. We have a functions, so you use the fun keyword to say I'm a function. So this is something I don't know, my brain just stalled. Okay, so we have a function, and function returning a hunger level, which is of type unsigned 64. And we can set a hunger, again, defaulting the argument coming in. And where it gets interesting is this assignment, it's not really an assignment at all. So in most languages, when you assign something, you assign the value on the right to the value on the left, and we're all good. In Pony, when you assign the value on the right to the value on the left, and you chain it to the value further to the left, it gets the value that was in the value in the middle before you put the value in the right into it. So the value on the left now has the old type, or the old value, so we've done a swap without a temporary variable, because it kind of chains along. It's a destructive read. What you return is the old value. Make sense?
Why doesn't that have brackets?
Are there any precedence issues here?
Oh no, my head's exploded.
We even optimize out the brackets where they're not needed. Because it makes sense. So native integration. Who's ever done native integration with JNI or NIFs or BIFs and Erlang? It's awesome, isn't it? It just works. So native integration. No? It's just as easy in Pony. In Pony, we use a Twitter-like syntax. So if you put an at in front of a function, what you mean is, can you call, in this case, sprintf? And it goes, oh, yeah, that's in standard I/O. Here, have one of them. That's kind of pretty cool. You're integrated. That's it. So I might have an actor, and I'm going to go, hey, I want to go the other direction. Can I send this over to Sealand? You go, yeah, sure. Just, tweet it over to the other side of the language boundary. So it's like Twitter. Twitter integration. Yeah. Finally, we found something useful to do with Twitter. So yes, Pony actually uses a C ABI underneath, so a valid Pony program is also a valid C program, so it just works. It's awesome. And this generates a really large library you need to integrate against. It's very complicated to penetrate. So this very simple one line of code has mainly boilerplate on 1 or 2 lines of useful code in this massive 97-line header file, which of course will be very difficult to integrate into your native programs. That's pretty cool. Okay. There's so much more we can cover about the basic language, but we're here to talk about actors, not the awesome expression language, the statements that are expressions, and everything like that. So we could have covered generics, and we have object literals and lambdas, which means we have higher order functions. A lot of the sugar, for example, on create, and a bunch of other things, delegates, but we're going to stop there and move to something a little bit more interesting. We're going to go straight to micro-benchmarking and see how much Sylvan has been lying to us about the awesomeness of this fast, safe, and cheap language. Because we're all scientists or mathematicians or engineers here, so we all start from a point of distrust. So he's lying, so what better place to start than Fibonacci? It starts with a lie, right? Well, it makes sense. Well, what else are you going to choose? We could have used a golden spiral, it's just not as funny. So here's imperative fib. There's only 3 people in the audience that understand this. So let's skip it. It's not really very interesting. It could be fast, but that's fine. Let's write some tests and find out. Here's a non-tail recursive version that's more Erlang style in terms of pattern matching, so we'll reuse that. Yeah, I automatically understand what this means. I don't have to decrypt it anymore. It just perfectly makes sense, right? So if I have fib0, well, fib0, 0, so there you go. Return, get out of here, we're done. If I have fib1, well, yeah, get out of here, we're done. Otherwise, let's fib. Awesome. It's so simple. And then we have the tail recursive style. So you've seen underscore for a variable makes it private. Well, if you have underscore in front of a function name, it's now private too. So fib iter will be called if fib is non-zero. There you go. That's the tail recursive form of the same function. So can anyone guess as to relative to each other, which one is faster, which one's slower? So who thinks the imperative style, because JVM is awesome, C is awesome, will that be faster or slower than the non-tail recursive or the tail recursive form? Anyone hazard to take a guess?
Slower. Recursive will be slower. That would be fastest because it's not.
And will the Java version be faster than the C version, or? I'm not expecting you to write the code. I've already done that. We have slides. So we just move forward? Okay, cool. It's your conference. So here we go. So I implemented these 3 functions in Pony, in C, in Java, and in Erlang. So we noticed that for the non-tail recursive form, we're skipping imperative, by the way. You'll see why in a minute. And we call that, is 1x. So Pony's the fastest. And C is only 34% slower. That's pretty cool. C isn't that bad. It's not as fast as Pony. Java, on the other hand, is 7.8 times slower. That's reasonably bad. And Erlang is different, so this is more apples and oranges. Have you ever gone to a talk and an Erlang person says, well, comparing is apple and oranges? So these are using 64-bit integers, right? It's fixed. Whereas Erlang, you can have any depth you want, you can have any precision. It's infinitely more flexible. Now, clearly, you have to pay for this. It makes sense. So it's a bit slower. So now let's compare Pony to Pony, because relatively speaking, we can see that if you're a good functional programmer, you won, no matter what language you choose. That's just relative. Right? So whatever. Functional programming wins. Bad functional programming doesn't win as much. Let's just focus on Pony again and see if N37, so fib 37, 10,000 iterations, happens to be a benchmark unit of 1, right? So that doesn't matter what machine you run it on. Then the non-tail recursive form compared to tail recursive is 66,000 times slower-ish. I've rounded it. But the imperative form is 15% worse than that again, which is why you really shouldn't use imperative programming. It's bad for you. This is much better if you use functional programming. And if you want to sub-optimize again, just use Pony, because it's faster, at least at the moment. Now everyone has to catch up. That's pretty cool. And like, it's totally new, so they're not working around all the bugs in all the older languages, and that's why it's faster. That's why it's faster, isn't it? He said yes. So anyway, enough lies. On to actors. So who here knows about actors? No one. Okay, so this is a new subject for everyone except Sylvan. So they're basically just like classes. They can have behaviors, right? That's pretty simple. Joe's been saying for years they're object-oriented. Like, here's proof. Yeah, it took a few years. So actor behavior. So behavior is basically just an asynchronous function. And when a behavior is called, it's not executed now. Remember, it's asynchronous. It might happen at some point in the future. And you'll see why later why we don't care. We do care that it happens recently in the future, but not right now is okay because it's asynchronous.
Recently in the future?
We'll see later why that doesn't matter. Well, with Pony. It does with the other actor implementations, but yeah, that's like an advanced subject, which is a couple of slides on. So it does need a receiver capability. Again, this is where Pony is different. So we have functional programming cells, and we have types, but types there's something else in Pony that wasn't different enough for Sylvan, so he came up with capabilities. So you need a type and a capability to do something useful in Pony. And the real genius of this extra capability, which is entirely predicated on denial, which is why it's weird and awesome, means that we don't have to manually kill our actors. The runtime can do it for us. So just like the JVM gave us memory management, Pony took it away. So you don't have to manage your actors. You don't have to kill them. Pony knows when they're not useful anymore, they're beyond serviceability, and it puts them down for us, which is extremely powerful. So if you have problems managing binary heaps and all this kind of stuff and other actor models, well, Pony doesn't suffer from this. It's just, you're dead. Just kill them. Send them away. It's pretty awesome. So in this case, we have a little ping pong actor which takes a reference to itself and then starts pinging and ponging itself, which if you run and scale it across multiple cores, it's pretty interesting how you see it's got exactly the same kind of deterministic scheduling that Erlang does. It's pretty good, and that's totally the entire program. And you can play with it with some of the tunable options in Pony and have some fun and see how it scales on your laptop. Highly recommend that. So concurrency, as the behavior is asynchronous, many can be run at the same time. So each thread can be executed an actor behavior and any given time, and we don't care because we're using natural concurrency. So again, our three imperative programmers hiding in the back. The great thing about imperative programming, and JVM and C and C++ is we have blocks, and we have threads, and they don't compose. And when hardware changes, we have to rewrite all of our code. We don't have any of these benefits with the actor model. We use natural concurrency. Natural concurrency, when you first use it, is actually very, very difficult to use. You have to suspend disbelief for a moment and write code that seems natural and regular and uncomplicated and simple. And it's crazy. It kind of just works, which is pretty awesome, we think. And we think the imperative people would like that. They should play with it. So actors, when we're thinking in the box, we can think sequentially, and that's pretty awesome. But, we have these massive multi-core machines, we want to get some advantage, so just spin up more actors and let Sylvan's compiler and runtime worry about scheduling all of that stuff. So that's what we do. And that's what Erlang does, and that's what the actor model gives us. That's why the actor model is so awesome. And again, really the unique key difference is the actors get GC'd for you when they're finished their useful lives. They just, they get killed off, basically. It's brutal, but your memory, your machine, and your runtimes will love you for this. So this is great DevOps. It's pretty cool. So fast, safe, and cheap. So how cheap are they? Well, 240 bytes cheap, which I think is pretty cheap, right? Who thinks that's not cheap? Right answer. This is pretty cheap. There's no locks and no context switches, so all mutation is local. And we'll see how that was achieved later. So an idle actor consumes no resources, except for the memory. And when it's not running, it's literally not running, so it's not costing you anything. And you can have as many as you want, or as many as you can afford memory. So if you're using a new, what's it, the Xeon X3, Martin, we're talking about, with hundreds of cores, and 2 terabytes of memory, you can have like gazillions of actors. That'd be pretty awesome. So the compiler that says no, how does all this magic work? Now, there's 2 parts to this. There's the compiler that says no and why it says no, which is denying you everything. But once it's denied you everything, it can prove you're deadlock-free, data race-free, so you can write whatever you want. That's pretty cool. It has a proof and everything. It's encrypted in some mathematical language I don't understand. So Sylvan and a few other folk in the audience can help you read it. I'm happy just writing tests and using the runtime. So it's memory safe. There's no dangling pointers. No hoary nulls. There's no concept of null in Pony. We call it none. It's an atom. You can't zigzag an atom. Like they're entirely safe. It's nominal. It's like, hey, I'm nothing. You can't dereference it. It doesn't exist in the real world. It's a figment of Pony. It's pretty awesome. And the type system ensures it compiles down that your program really never data races. There's no deadlock. Because it doesn't have any locks. So it can't deadlock, and it won't deadlock. So it's pretty easy to write code that just works, that just scales, and you can make sense out of it without requiring a quick phone call to Martin Thompson, which is really very handy for the 3 imperative programmers. Oh, sorry, 2. Martin's here. Sorry. Well, but there's a problem. Nothing is perfect, right? Nothing is for free. What if Sylvan hates this slide? I love this slide. He doesn't know why he hates this slide. We'll just find out in a few slides. It's asynchronous. We have a behavior. What if, in this asynchronous behavior, we run a forever loop? There's this other awesome thing in Pony called causal messaging. So if I spin this behavior and I send another message to the actor and it's running the loop forever, how will that other message ever get in? It won't. You wrote bad code. So although Pony can prevent you from most things, you can still write bad code. It makes it really hard to write unsafe, bad, terrible code, but it's still possible. We don't recommend you write bad code, and this is probably the only bad example I could think of. And believe me, I've tried. I tried to get the machine addresses through a fluke call through FFI, sending it out as a printf, and the compiler said no. So I tried wrapping it in a variable, ephemeralizing it, sending it somewhere else, and using it as a local parameter, and the compiler said no. I said, no, you can wrap it, you can change it, you can swizzle it no matter you want, but you're not getting the hardware address. I'll give you its identity, which is the same, but you're not getting the hardware address. You don't need it. I still disagree on that, but we can talk about that later. It's fine. So there's 2 ways we could possibly run this. It makes any reasonable sense. We can try and kill the actor beforehand, and Pony will notice that it can't receive any more messages because nothing can possibly be sent that will ever get processed, so it'll kill it for you. Or we can run the loop first, which means we'll never be able to kill it. Either way, that's not a very useful program. So these are the 2 styles in which you shouldn't write Pony. It's only a list of 2. It's pretty small compared to most other programming languages, which is pretty cool. So Pony actors support causal messaging delivery is the real serious point behind this. So I actually can't say it or express it that well, so I'm going to use Sebastian Blessing's quote from a string of ponies. So when we get this distributed multi-node pony, I highly suggest you read this paper. And he says each message is an effect. And previously sent or received messages are a cause of that effect, because the cause can't happen in the future. So causal message delivery guarantees that the cause of a message is always in queued in an actor's mailbox before its effect. Who disagrees with this? No philosophers. I can't find a way that you can disagree with this. So if you want to find out how the garbage collector can leverage this, why this is the killer feature and why everything inside Pony is so awesome and worth learning, is how the garbage collection can actually work with this Using deny capabilities, which we're just about to step into, it's the easiest part to learn about Pony. Scares the hell out of me, too. I highly recommend reading this paper, too. So Pony is basically formal proofs, and it's the representation of those formal proofs and the protocols inside the language and runtime basically make it safe for us to write code that he prefers to write, and we wouldn't. Because we've got stuff to do. So capabilities in a nutshell. So a capability, for example, an object capability in JavaScript or anything else, it's pretty simple. The imperative people understand this because they have objects, and functions we don't. We just, object is a function, I guess. But if you have a reference to an object, you can do stuff with it. Fair? If you don't, what object? You can't do anything. This is pretty cool. But if you have a reference to a thing, or a capability, it gets slightly harder. So to describe access rights on an object and whether I can invoke a function that mutates a field, for example, so that I have isolation guarantees or I can share a thing is much more difficult to express. It's also harder to prove. Glad I didn't do the proof. So what do we want basically out of the system, and why do we attend conferences like this? So shared mutable data is hard, agreed. Mutable data is safe. Safely shared, agreed, but sometimes mutable data that we can share is more performant, even though it's a bit dangerous. But isolated data is certainly safe. It may be complex, but when every actor is single-threaded, there's a path to solving this problem if we're strict about the way we interact with fields and mutable variables inside our programs, or inside the actors running in our programs. And this is really what capabilities are all about. And the most important capability is isolation. So this is read, write, and unique. So if you imagine that you got a number of actors and they all have a reference to a thing. Can anyone think of why this might be bad? Well, it's not isolated. Multiple actors have a reference to a thing. So we're going to have a look at this in a second with a few examples. It could be immutable. That's the other extreme. So if it's immutable, you can't change it. So it's safe to share. It's safe to read. You can't change it. It's immutable. So it can be a reference. So a reference is kind of like regular imperative code where you don't have the benefits of single assignment, where you can change things. It's exactly the same thing. So you can change it whenever you want. All the threads can change it at the same time, and everything just works, right? No deadlocks. Data race free? No, it's the exact opposite. Then Pony kind of gets weird. So these are the things we expect, and then we have a boxed type. So it's readable to you, but it may be readable or writable by others. It doesn't really roll off the tongue, and it doesn't roll into the head very easily either. You have to spend a couple of weeks digesting this one. A transition type. It's got the most awesome name in Pony. I think only Sylvan understands this one. It's write only. So the variable references data we wish to share as read only to others. It's what? We can't read it ourselves?
It's write unique.
It's
So
write unique.
it's the only writable reference to something that may be readable by others.
Which can be made into an immutable later. Yeah, so that can be turned into a value. Still don't know why. Or it can be a tag, which means it has an identity. Okay, so it doesn't really deny you anything, so you can't really send it anywhere because you can do anything to it, and it's not safe to read or write. Make sense? It's pretty simple. So what can be safely sent in a message by reference? By preserving all of these nice guarantees. So isolation or immutability or identity. And that's really the secret sauce inside Pony that enables everything else to just work. And that's what we're going to dig into. So what permissions do we need to be expressed? Well, there's writability and readability. There's this new thing that Pony introduces called aliasing. So if I pass a reference to something potentially readable or writable, and the compiler knows who that's being sent to, then the compiler can check and do an exhaustive search to see what the scope of this mutability is across the mutations in the data flow and the code paths. So if you try to do something bad with something we said should have been isolated, the compiler can say no. You said you wanted an isolated reference, and if I give you a reference while I maintain a reference for myself, I violated that guarantee. So think of a relay race. This is like the Olympics for programming people. You have one token to the isolated object, and you pass a reference along to your different objects. And if you have the reference, you can do things with it. Otherwise, you can't, because you have to sacrifice the reference. And ponies are called ephemeral types. So let's say we have Alice and Bob are accessing some shared data. So Alice has isolated permissions, and Bob has no permissions on the data. So this is OK. So Alice can pretty much do whatever she wants in the context of isolation. So she can send a message, or she can do various stuff. But Bob can't really do anything other than have a reference to it. So if Fred, however, or Wilma have an isolated reference or a writable reference, some other reference type that can read or write into that same shared piece of data, then we violated the isolation guarantee. So the compiler says no. And the compiler builds these lovely graphs of code for you at compile time and selects out the ones that are true and gives you a compiler error for the ones that you accidentally tried to program that it doesn't think you're mature enough to use. And the compiler is always right, except when it's wrong. So that's the isolation capability. So here, I'm not sure it's easy to read the diagrams at the back, but basically, if you try to write and read at the same time for something that was supposed to be isolated from more than one reference, you've clearly violated a guarantee. So Pony ensures that all of these guarantees essentially are preserved despite providing a very flexible environment to write programs. So this prevents any data race or deadlock or any of the other conditions that become possible if these guarantees weren't provided, if that makes sense. Sylvan can also explain this, but it takes 4 hours. And then we realize we're late to get home and we're going to get in trouble by our wives. But it does take a couple of weeks to get used to all these 6 different capabilities and how they merge together. So, for example, tag, a reference to an object doesn't have to make any guarantees about aliases. That's great. So it's basically not very useful except for actors, which is where it's primarily used. So because they're asynchronous and mutation is local, tag identity to the actor is enough to be able to invoke a message against it, send a message to it, or receive a message from it. So that implicitly should make sense. So how does all this crazy capability stuff work? It turns out that Sylvan spent a couple of months, years, days, maybe an hour. That was years. Thinking about how these compose and did some formal proofs to see how to make this simple for the rest of us, so people like me, us Padawan learners. And it turns out, if you look at the local guarantees, so I am the actor and I have local access to these fields, versus global guarantees, I am something referencing the actor, which may or may not have a capability to read, write, or identify, then how does that construct? So for isolation, locally, the read-write deny capability, it should be exactly the same as globally. It's isolated, so only one actor at a time should be able to read or write. It's read or write unique. For a value or an immutable type, then we deny write capability locally and globally in exactly the same way. It's immutable. You can't write to it locally. You can't write to it globally. It kind of intuitively makes sense, but it's the opposite way of thinking that we're normally used to. And finally, if it's a tag, we don't deny anything. Make sense? So these 3 together are the 3 sendable types within Pony. So if it's isolated, if it's a val or an immutable type or it's a tag, you can send it from one actor to another. Everything else is banned. So all mutation is local, which pretty much makes it safe. Does that make sense? It's a complex mechanism with a very simple result. Working through the rest of the matrix, you need to transition, which I don't understand, box, which I slightly understand, and reference, which is obvious. That's the imperative style of doing things. But it only allows you to do it in a good way in Pony. So if a function is a reference function, you can mutate the fields in that class or in that actor. If it's not a reference, you can't. Except in a behavior, because it's always local, you can always access, mutate, or read the variables within the actor. But when you pass a reference to another piece of the system, then the capabilities essentially come into play to determine what you can. There's a very simple relationship for this in terms of deny capabilities. So you can see on the right-hand side, we deny nothing. On the left-hand side, we pretty much deny everything except the ability to send a reference from one place to another in a read-write and unique fashion. And we've run out of time.
Go fast, go fast.
I can't do that fast. It's your turn. It's supposed to be our talk. go.
What, art? Are you kidding me? Does anyone know who this guy is?
About half the audience.
Right, so apparently I'm covering the runtime in 1 minute. Here we go. So, right, I don't know what the hell Darach's doing with this.
There, your notes. I didn't
Here we
see
go.
yours.
No, I think, oh, did you
Go
cut all the
down.
garbage collection stuff? Thank you. The actors, right, so actors are actors, that's good. Is there anything you want to say about this stuff? No, let's keep going. We don't have enough time. No, you know what, I'm just gonna wing it on some of the garbage collection stuff because you didn't put it in there. And this is
That's
good
fair.
stuff. So find the stuff, excellent. All these deny capabilities are fun, and we want to make these guarantees. Of course, we already make them as programmers when we write code. We don't have a compiler that enforces them, but it's how we think already about ownership of data and sharing of data. But having all this stuff where we can prove it to the compiler is awesome, because now we have a garbage collector that is aware of this stuff. So now we have a garbage collector that's a no-stop-the-world garbage collector. There's no thread coordination ever during garbage collection of any kind. That's pretty fun. We also have no read or write barriers during garbage collection. That's pretty fun. We also never touch anything but the working set, right? So we only trace the working set. There's no sweep phase on the garbage collector. That's really cool for cache reasons. There's no card marking. There's none of this overhead that you have in languages that don't have a strict semantics like this, right? Not that those garbage collectors aren't good. They're awesome. They can garbage collect for semantics that this could never garbage collect for. But because we don't have to, it can be a lot faster. That's pretty interesting. It's also that protocol gets extended to collect the actors themselves, so that we determine when an actor's message queue is empty and when it will stay empty for the remainder of the execution of the program. And that means at that point we can garbage collect the actor itself, which is pretty fun. Scheduler layout, pretty much what you'd expect. SPMCQ schedulers, let's go. Right, 0 atomic operations to put an actor in a scheduler queue, cas loop to pop it out, but that's only during work stealing, so that's pretty good. 1 atomic operation with no cas loop to put a message in a mailbox, that's good, right? That's just an exchange in the underlying code, and nothing to get it back out again. So that's pretty good. On the other hand, these are unbounded queues, so we're not making a back pressure guarantee. So that's, wait a minute, is that good or bad? Does anyone have an opinion on that?
Yes.
Hopefully you all think it is both good and bad. All right, let's keep going here. Right, FFI with LTO, I think you covered that a little bit. We literally can do LTO level compilation with native code, which is nice, in both directions, with Pony as a library or Pony using C++ libraries. Let's go. Right, I already talked about this because he was right and the slide was there. Let's go. I don't know what that is. Let's go.
This was Pony for Joe. So Pony is a language. We have all the bits, but we're missing OTP, so we're adding it, essentially. Monitors and links are missing, so all the systemic features in Erlang that we know and love are missing in Pony, so they need to be retrofitted. A state machine model. Gen server and Gen NB server for non-blocking or asynchronous. That's basically a Pony actor. That should be obvious that that's built in. But monitor, link, and supervisor are really the core missing components that are going to be added. So Gen FSM I'm actually fiddling with, so that should be there soon. And in the standard library, other things will come along as well. Gen event was so easy to implement. We implemented it. It's in the slides, but we just skipped over it. So if your eyes are faster than a trader's, you've probably caught it and implemented it while we got here. So that's awesome.
Just to touch on distributed Pony, it's vaporware. We have a prototype. Sebastian Blessing's thesis has all these proofs that we can do it. It's not ready for prime time, so don't jump in and think we can do it. We will be able to do it, but not yet.
You want to go through these?
Type specialization, okay, so these are some things that are going to be added. I think we got to get off the slides. I think we're going to get murdered here.
Yeah, Voodoo's going to make me text for you in a minute.
That's fair enough. So there's all sorts of things that are coming, more type system madness. Being able to write proper function signatures, yes, that'll be in soon. Right. Please, please, please have a look. I'm desperate, come on, have a look.
It's lonely being an only Pony.